In previous lecture, we have derived the expression for torque acting on the rotating body and angular expression for angular momentum of the rotating body. Now, today's class we are going to see the next point, that is conservation of angular momentum. In previous classes, we had learned about conservation of energy. What? Energy can neither be created nor be destroyed. Same way here we have to study about conservation of angular momentum. Okay. So what is conservation of angular momentum? Angular momentum of a body is conserved. Statement. Note down the statement. Okay. Angular momentum of a body is conserved when external torque acting on body is zero. What is the statement? Angular momentum is said to be conserved if external torque acting on body is zero. This is the statement of law of angular momentum. Now we have to prove it. Okay. So by definition of angular momentum, what is definition of angular momentum? It is a vector product of radius vector and linear momentum. So L is equal to R cross P. So I have written here L is equal to R cross P. Now differentiating this, that means taking the derivative of the above equation. So taking the derivative, what we get? D by dt with respect to time. We are differentiating with respect to time. So dl upon dt is equal to d by dt of this product. Now here we have to use our product rule of the derivative, that is u into v. What is u into v? U as it is derivative of v plus v as it is derivative of u. So same we have here u as it is, r as it is derivative of v, that is derivative of p, and here v as it is, that is p as it is, and derivative of v, that is derivative of r dr by dt. Okay, this is a product rule of derivative. So r derivative of p plus p derivative of r. Okay, now derivative of p is linear momentum. So when we differentiate linear momentum with respect to time, we get force. So I have written here dp by dt is f. And what is value of that linear momentum? In the previous lecture we have discussed that linear momentum is product of mass into velocity. Linear momentum is product of mass into velocity. So P is equal to mv. Now next, the derivative of radius vector, as radius vector is changing, which is giving a displacement with respect to time, and displacement with respect to time is velocity. So rate of change of radius vector with respect to time is velocity v. So I just substituted that value in this above equation. In place of dp by dt, I have written f. In place of p, I have written mv, and in place of dr by dt, I have written v. Okay. Now, again in the previous lecture, we had studied the torque. What is torque? It is a product of radius vector into force. Okay. So R into F is torque to your M and V cross V. Okay. Now R into F is torque to, so I have written here to. Okay. And what is V cross V? We have studied the vector product. Vector product with itself is always zero. So V cross V is zero. I have written it here. So what we get? dl by dt is equal to tau. But what our statement says? External torque acting on body is zero. So tau is equal to zero. So if we put, we get dl by dt is equal to zero. And when the derivative is zero, if derivative of constant is only zero, we had the formula derivative d by dx of k, where k is a constant, is zero. So if the term is constant, then the derivative becomes zero. If term is constant, then derivative becomes zero. So that means here derivative is zero. So the term L must be constant. So we had written therefore L is constant. Understood? So only the dl by dt is zero because L is constant. Okay? So we have to prove with help of this class. These three steps are important. What we get, dl by dt is equal to 2. But by the statement we have torque 2 is equal to 0. So I have mentioned here 2 is equal to 0. Now 2 is equal to 0. So dl by dt is equal to 0. And when derivative is 0, if this n is constant, so if n is constant, then only dl by dt will be 0. So from that I have written that L is constant. This is proof of law of conservation of angular momentum. It is asked for 2 marks, or with statement it can be asked for 3 marks. Okay, but mostly it is asked for 2 marks in board exam. Okay. Now next, expression for kinetic energy of rolling body. Now what is rolling body? What is rolling motion? Okay, already we have discussed what is rolling motion. See, when body is rotating here, it is performing two kind of motion. Okay, it is rotating with itself and it is covering certain distance. Okay, so there is linear displacement as well as angular displacement. It is rotating. See. Okay. So such kind of motion is called as rolling motion. Now we have to find the kinetic energy of body performing rolling motion. Okay. So when body is rolling, it is performing two kind of motion: linear motion and rotating motion, rotational motion. So the kinetic energy of rolling body is equal to kinetic energy of a body performing linear motion plus kinetic energy of rotational motion. Okay, because it is rotating with itself. See here, here it is a tire you can consider, or ball you can consider. It is sliding down. So it is rotating with itself and it is covering this linear distance s. Okay. So the motion, there is two kind of motion. So the kinetic energies again of two motion, that is of linear motion as well as rotational motion. Now, what is the formula for kinetic energy of linear motion? Half mv square. We are studying since very smaller standard, okay, lower standard. And kinetic energy of rotational motion, we have derived first expression. Okay, so what is that? Half I omega square. Okay, so half mv square plus half I omega square. Now we have the relation what? V is equal to R omega. So from that we have removed the value of omega. Omega is equal to V upon R. Omega is equal to V upon R. And also we have the value of R, where I is moment of inertia. Moment of inertia is product of mass into square of a distance. So I is equal to mk square, where k is radius of dilation. Okay. So I is equal to mk square. So put this value in this equation. So what is our equation will become? Half mv square as it is. 1 upon 2. In place of I, we have to write mk square. So written mk square, and omega is equal to V upon R. So V upon R bracket whole square. Now just simplify this term as it is. Now I have taken this term before this. So m as it is, I shifted this k square that side. So half m v square upon R square into k square. Now if you observe in both this term, half and v square is common, so I have taken outside. So what is remaining? In this term, there is nothing is remaining, that means 1 is remaining, and what is remaining here in this term? K square upon R square. So k square upon R square. Okay. So I got kinetic energy of rolling body is nothing but equal to half mv square into bracket 1 plus k square upon R square. This is the expression for kinetic energy of rolling motion. Note down. Okay. Now we have removed the expression for kinetic energy of rolling motion. Now we are going to remove the expression for acceleration of rolling motion. Expression for acceleration of rolling motion. Okay. Now see, consider particle is here. So initial velocity u is 0. Okay, and final velocity here it is v. Okay, and displacement as body is moving from here to here, so displacement of by the particle is s. Okay, and it is inclined by certain angle theta. Okay, and the height is h. Now as particle is initially here, so it has potential energy. Okay, and finally by rolling it has come at this place. So while during the motion, the energy possessed by the particle is kinetic energy. So I can write potential energy is converted into kinetic energy. That for potential energy is equal to kinetic energy. What is potential energy formula? mgh. And what is kinetic energy formula of rolling motion? Just we have derived now. Okay, that is half mv square into bracket 1 plus k square upon r square. So I just insert it here. Okay, potential energy mgh and kinetic energy half mv square into bracket 1 plus k square upon r square. Okay, now m and m get cancelled. These two move to that side, so we get 2gh, and this bracket here it is multiplying, here it will divide, so we get 2gh upon 1 plus k square by r square equal to v square. Then by kinematical equation, what we have, v square equal to u square plus 2as, v square equal to u square plus 2as, therefore 2as equal to v square minus u square. Therefore, A is equal to v square minus u square upon 2s. Just simplification of this kinematical equation we have done. Okay. Now put the values. What is value of v which we have obtained? V square is nothing but 2gh upon 1 plus k square upon r square. So 2gh upon 1 plus k square upon r square in place of v square minus u square. What is u square? 0. So u square is 0 upon 2s. Okay. So upon 2s. Now, from the figure, again consider the figure. Okay, this is the angle theta. So if we apply here sine of theta, what we have? Opposite upon hypotenuse. What is opposite? H, and hypotenuse is s. So sine theta is equal to h upon s. Therefore, I get h is equal to s sine theta, and this value I am substituting here. Okay, so when I will substitute here, so what I get? 2g. H is s sine theta upon 1 plus k square upon r square into 2s. Now 2 and s as get cancelled. What remain? G sine theta upon 1 plus k square upon r square. This is the expression for acceleration of body performing rolling motion. Understood? This is the expression for an acceleration of body which is performing rolling motion. Note down.